Good afternoon all. Let's continue the discussion over the antenna parameters. In the previous class, we have discussed regarding the gain of the antenna. I'll just show you. Uh, Gain as well as directivity. We started actually with the radiation intensity, then beam efficiency, directivity. Directivity, we have derived one formula as well, D equals to 4 pi by omega A. Then gain, capital G, and some formula also. With that, some basics regarding this manipulations of directivity we have seen. D is equal to, taking some example of HPBW as 20 degrees, we have seen the significance of gain. Then we have solved one problem. I think this was the homework given to you. Both these integrations, you have to find out these values, how we got this. Okay, I hope you have done this. After this problem, then the last parameter we discussed was directivity and resolution. We have seen the resolution of an antenna. It depicts the quality. It is equal to half the beam width between first nulls, BWFN divided by 2, which is approximately equal to HPBW. And we were just discussing about this. If there are n different transmitters which are there distributed in the sky uniformly, then if an antenna can resolve this, if you just see this 4 pi by omega A is equal to what? Directivity. We have derived this formula. So directivity and resolution, that is capital N, both are interchangeable terms sometimes. So ideally, number of transmitters of an antenna that can be resolved, it is equal to, numerically it is equal to the directivity. D is approximately equal to capital N. N is the number of transmitters that can be resolved. So how much clearly they can be made visible. Fine. Then in the today's class, let's discuss the antenna apertures. Okay. What exactly aperture is? This is a familiar term to you. You tell me where you have studied this aperture concept. What is an aperture? I think in physics you might have studied this aperture. In which topic you have studied aperture? You can unmute and answer me.
Physics only, ma'am.
In physics, yes, answer. Somebody has answered. Tabassum. Lens, optics, correct. In physics, when you're dealing with the lenses, their aperture concept has come. So it is familiar with you. So what is an aperture? Anybody?
Hole, ma'am.
Hole. Okay.
Which allows light to pass, ma'am.
Yes, sorry.
Which allows light to pass.
That area is that hole what you're talking, in a very specific terms, that is called the area through which the light passes, right? So here also antenna aperture indicates the area. Okay, antenna, obviously some physical construction should be there for an antenna. In order to use it as a transmitter or a receiver, we should have certain design. And if we construct an antenna, there will be certain area in the antenna through which the power radiates, through which the electromagnetic waves come out, or the electromagnetic waves, the power gets received. That particular area we call it aperture. Okay, so aperture of an antenna, it is the area through which the power is either transmitted or received. If you can see, this is one example of antenna. It is called horn antenna. It looks like a horn, I guess. Okay, it's a horn antenna. If you see, this is the wider mouth of an antenna. This is the aperture of horn antenna. Okay, so here I have given horn antenna and parabolic reflector. Parabolic, it is the shape of that antenna. A reflector is the term which we use for antenna. So reflector is nothing but antenna. Okay, it is both are interchangeable sometimes. So these are the horn antenna and parabolic antenna, and there are many few antennas. These are the examples of aperture type of an antenna, wherein that area is very important for the operation of the antenna. Okay. If you see this figure, what you can make out from this figure? Any observation is made? You forget about this. Okay, here probably it is not clear, but at least the same cross section I have drawn. Okay, the same thing, cross section I have drawn. Somewhat this is the mouth area of this antenna. Probably shape is different. So what observation you can make by looking at this particular antenna? Check the directions and tell me.
Wave
Sorry, you're not.
direction.
हाँ, direction देखो, direction देख के बताओ. Any observation, any point to be noted? Anybody? Unmute and answer, no problem. Check the direction and observe some point. Anyone? Quickly, we are running out of. No one, no observation? Look at the figure, look at the direction of power W and tell me any observation you can make it. It's very simple actually. Yes?
Conversion, ma'am.
Conversion. Somebody said something in between. I could not hear it.
Receiver.
Yes, who's this?
Me, ma'am, Rumana.
Rumana. Rumana, very good. You have observed it well. It is a receiver. Okay, no doubt it's a type of antenna. One horn antenna we have taken. If you look at the direction, some power, probably electromagnetic waves, they are getting received here. So this is a receiving type of antenna. That is the first observation. So for antenna aperture concept, in order to explain that, we are making use of a receiver. Okay, let's proceed. In order to understand the aperture, let's see how we can utilize this structure, and we will try to represent this in a form of a circuit. Okay, we'll just make use of little bit network theory and we'll see what happens. Coming to next, this is the figure. Remember this. Consider an antenna used as a receiver as shown. W is the total received power. We don't know what power a transmitter is sending. Generally, W is the notation we used to indicate total received power. Okay. In this total received power, if at the mouth W is the received power, this is the load we connect at the end to get the output, right? You know this in network theory. Whenever you take out, even in your lab experiments, when you take out the output, so you connect a load at the end. Okay, so in order to check the output, this whatever W has received at the mouth, it will not be the same which a load will receive. W, this total amount will not reach. Okay, this is very obvious. You can check it in the figure. Out of the total power received, a small portion gets scattered. When it reaches the mouth, some may get scattered. Scattering means what? It's a very common phenomenon. Scattering, when it touches any surface, it will change its direction, right? So it may happen that due to the structure, dimension and shape, some of the power may get scattered. It will not enter the mouth completely, it will get scattered or radiated. A small portion it gets lost because the material which we use, it is also important to design the antenna. Even you have seen in case of ICs, when you're dealing with digital electronics lab, when you know switch on the kit for more amount of time, longer time, your IC gets heated. Okay, the heat dissipation occurs. It's a very common phenomenon. So some amount of power may get lost as a heat, and the remaining power scattering, after getting scattered, after getting lost as a heat, some amount of power, say W suffix E, it is then supplied to the load. That's what W is entered, the end product is WE, and E is the suffix we use to denote effective power. Okay, let me give you one example for this. Try to imagine a pineapple. Okay, when you buy a pineapple, get to your home to eat, you cut the pineapple. Whatever weight the pineapple you have purchased, say assume you have purchased some 2 kg pineapple in weight. When you cut it into pieces, when you just remove its covering and whatever all the skin part, the amount of the actual eatable, the edible part of the pineapple, it will be less. Okay, removing all those skin and all, the 2 kg pineapple, probably you'll be left with 1.5 kg pineapple. It's like that. So all these losses, scattering, it's like a skin which you cannot eat. So the only the effective or edible part will be left out, that is the effective part. So I hope you understood the example. So let's proceed. Now, just observe this figure and this figure. Okay. This is a receiver. Power gets received and load is connected at the end. The same thing is shown in the equivalent circuit. Check it. This is the supply voltage. In order to get the power, definitely whenever it is a receiving antenna, okay, any antenna or any, you have seen this in network theory, whenever any device you take or connect, associated resistances you take into account. So that resistance part is denoted as Z suffix capital A. A stands for antenna. I would have used capital R directly, but in an antenna, the impedance Z, it will be, you know this, it is a combination of resistance plus reactance, right? That's why in general I have taken capital Z. Then further we will substitute this. So generally it is ZA, indicating the impedance for an antenna. So this is the antenna part. Now here load is connected at the end terminal. So as the load is connected, load will also be having certain impedance, that is denoted as Z suffix capital T. I hope it is visible, capital T. Why I have taken capital T? There is a reason behind it. The same circuit I have redrawn with the details of Z. You can observe here. V and I are the voltage and current. This is the potential difference and this is the current flow. ZA has got the resistance part and the reactance part. XA is the reactance, and there are two different resistances I have considered. One is RL, because at the antenna part, when the power gets received, in the meanwhile, there will be certain losses. So this indicates a loss resistance. Okay. And RR is the radiation resistance. RR. For an antenna, RR is the radiation resistance. So RR and RL. Now, why I have taken the suffix ZT? As A antenna starts with A, I have taken A. So as load starts with L, I would have taken ZL, then this would become RL, okay, and XL. Then we have already used RL for loss resistance. It gets confused with the load resistance. Because of this reason, we have taken ZT as the load impedance. T indicates terminal, okay, RT and XT. So this is the equivalent circuit of a receiver, and at the end we have connected the load. Now, taking this as a reference, let us see the further concept. This is important, okay, you should understand this equivalent circuit. Now, V is the induced potential difference across the antenna terminals. I is the induced current. So, according to the formula, current I is equal to V by R. R is the resistance, but here we have to take both resistance and reactance. So, I have taken capital Z. Now, for overall circuit, the total resistance will be, I have to move further. Yes, total resistance will be ZA plus ZT, right? ZA plus ZT. So replace this general impedance into both. The circuit has got two different impedances, ZA and ZT. Add them. Then keeping V as it is, what is ZA? Write it. Resistance RR plus RL. This is the real part, resistance part, and this is the reactance part, I into XA. This is for ZA, antenna impedance. Now, similarly substitute for ZT. It is RT plus IXT, reactance and resistance. So, after substitution, we will get this. Now, further, I is equal to, what I will do, there are some real parts and some imaginary parts. I will club all the real parts at 1 and imaginary at 1. So real parts, 2 terms plus 1, 3 terms. So add all the 3 plus I into, there are two different reactances, XA plus XT. So this is I is equal to this much. But as practically when dealing with the concepts, we try to avoid the imaginary parts. That's why we tend to take the amplitudes. So for amplitude calculation, keep the numerator as it is. How to calculate the amplitude of this denominator? Amplitude, say
Square root of a square plus b square.
square. Yes, if it is a plus ib, it will be square root of a square plus b square. So similarly, this is your a, this is your b. So square root of a square plus b square. This is your magnitude of the current flow. So this is important equation. From this equation onwards, we will deal with what are the different types of apertures available. Okay, let's start with the first aperture. It is effective aperture, A suffix E. Just like if you see here, we have WE, effective power, which is always less than this received power, total received power. So just like WE, so AE is the effective power. So how to get the effective power? So effective power, it is defined as the ratio of effective power divided by power density. How I got this equation? Let me just show you why I have taken this only. Okay, if you check this figure, this is the definition of power density. Remember, power density, the first parameter which we have discussed is the power density or Poynting vector S, which is given by the power radiated by area, W by A. So how to get the area? Area is W divided by P. Here I have written it. Area is equal to W by P. So this we have used. W is the power divided by power density. The same thing we are using in the definition. See, effective power W divided by power density, and the power is why WE, because we are talking about effective, so effective power. So AE is equal to WE divided by P, and the WE, that is power, is equal to I square R. So I square into RT. Why RT? Load at the end. Okay, effective will be at the end, right? Check the figure, it is near the load side. That's why the resistance counted is RT. I square RT divided by P. In this, RT and P I will keep as it is. Instead of I square, just now we have deduced one equation here. We have got one equation for magnitude of I. We'll take the I square. I square will be V square, right? V square divided by this complete denominator square. So square and square root gets cancelled. Whatever bracket term is there, the same thing has been kept as it is. Okay, this is the equation for effective aperture AE. Okay, now we will just analyze this final equation. What can be done? If you just think of any ideal system, then there, for any ideal system, hypothetical, losses are zero. So there will not be loss resistance, and the radiation resistance of an antenna and the load side resistance RT, okay, the antenna side and the load side, whatever resistances you are having, both are equal. This is the second thing. Then we don't have any reactance part for ideal system, only this real term exists. For that, just make this one is the negative of the other. So with that, this will go. So only real part exists. So with these conditions, we will see how this equation gets modified. Let's see. So AE will become, for ideal system, if you do all these substitutions, AE will become AEM. M indicates a maximum. Okay, AEM is the maximum. It is numerator. I have kept it as it is. You can't do anything. P is as it is. Now put the terms here. RR two times, because we have used this condition. RR equals to RT. Then this condition, this we should make it 0. XA and XT. So XT I have substituted on both sides. Yes, on both sides. I think I have done some mistake. Check it. No, it's negative. No, fine. Minus xt plus xt, this will go 0, you'll get. Now let's see what changes will be here. Numerator as it is, denominator p, rr plus rr whole square. So 2rr whole square plus this will go 0. V square by rr divided by this 2 square will become 4. P I have kept as it is, rr square. So it is, numerator we have 1 rr, denominator r square, 1 gets cancelled, v square by 4p rr. This is the maximum effective aperture AEM. We know this is the effective aperture equation. If you substitute for ideal system, it will become maximum effective aperture. Then as a note, I have written something here. See, effectiveness ratio, that is denoted as alpha, it is defined as the ratio of effective aperture to the maximum effective aperture. This is called effectiveness ratio, AE by AEM, ranging between 0 to 1. And for ideal system, both values are equal. But otherwise, for any practical thing, this will be always less, this will be more. You know, practical case obviously ये maximum है ideal system के लिए, that is fine. 1, but AE numerator will always be less, so that alpha range will always be between 0 and 1. So this is about the first type of aperture. Then moving to the second type of aperture, that is a scattering aperture. How we got this? Through this diagram, check it. We have seen this WE, so we got AE. Now we have WS, scattered power, so we will check AS, scattering aperture, and we have certain losses also, loss power WL in the form of heat. For that, we will see what is loss aperture. Fine. Three different types of apertures because of three different types of powers. Coming to the next, scattering aperture AS, it is defined as the ratio of, again, we have seen area is equal to, from the power density, W divided by P. So the scattering aperture AS is given by the ratio of scattered power to the power density. But in case of effective, you check, it is effective power by power density. Fine. So writing this, Ws by P, and W power is equal to I square into R, I square into RR. Why we have taken RR? This part, because we are not considering losses yet. Before the losses, we get scattering, and this is the basic resistance of an antenna. We have still not considered RL. Losses will come after you enter the antenna. Okay, after the power enters, then the losses. But before it reaches its mouth, there the scattering comes. That's why we take RR in the numerator. So RR divided by P. So then put the equation for I square just like the earlier. It will become V square divided by P as it is, RR as it is, and square. So denominator square and square root gets cancelled. So this is about scattering aperture AS. Just like the earlier case, alpha, effectiveness ratio, we have scattering ratio also, scattering ratio beta. It is defined as the ratio of scattering aperture to the effective aperture. Okay, how much it is scattered, then remaining will be your, after losses also, we will get effective aperture. Again, the range of beta, it is between 0 to infinity. Here it is 0 to 1, and for ideal systems, for an ideal antenna, the value is 1. Beta is equal to 1. Coming to the third type, we have completed scattering, we have completed effective. Now the loss. Loss aperture is defined as the ratio of power lost, WL, okay, due to some heat dissipation, to the power density, W by P. So here AL, loss aperture, is equal to I square into loss resistance RL divided by P. Again, numerator, it is I square is the magnitude, substitute V square RL divided by P as it is. Denominator square and root gets cancelled. Denominator is this. See here, the losses depends on the material used, then the shape of the antenna, and whatever dimensions of an antenna we are designing. So all these matter a lot. How much amount of power is lost, it depends on all these parameters. Okay, this is the third type of aperture. Coming to the next, it is collective aperture. As the word suggests, collective, all together. So how can we define it? It is defined as the ratio of the total received power to the power density. That is, in general, it is W by P, and it is given by I square, that is the W is given by I square R. This time in R resistance, all three resistance should be considered, because it is a total. We have to take into account of the scattering, then loss, and then effective all together when it reaches the load. So RT, RR and RL, overall circuit has how many resistance? You add all, will divided by P, and it will be equal to V square, and numerator bracket as it is, denominator power density as it is. This is square and square root gets cancelled. The remaining is this. This is about the collective aperture, A suffix C. Okay. So four apertures. One is effective, first one, then scattering aperture, then loss aperture, then collective aperture. And finally, one more aperture is there. It is physical aperture, that is physical, how the construction of the antenna is. So it depends on what? The shape, size and dimensions of an antenna. Just like horn antenna, just now I have shown you. The mouth is somewhat a square, right? Not square actually. How the mouth is, you can see this. Yeah, probably it's a square or rectangle. So inside that, how much part is available, how much amount of waves get into, the shape matters, size, shape, all these matter a lot when we design. So physical aperture, it depends on these parameters, and physical aperture is independent of this power of operation. Means we don't know how much entered, how much lost, how much scattered, but physical aperture is what actually what what is visible to you. That is physical aperture. As an example, you can see here it is the paraboloid type of antenna. This is the shape paraboloid, wherein this is the distance d. The physical aperture is given by pi d square divided by 4. This is the physical aperture for paraboloid. One more example is given here, linear antenna. It looks somewhat like this. TV sets के साथ जो आता था पहले, with many of the arrays like this. Okay, something like this. For this, if this is the length and this thickness is d, L into d will give you the physical aperture of this antenna. Okay, and one example is taken here. If L is lambda by 2, d is lambda by 100, AP will be L into d, lambda square by 200. AP is the mouth area for aperture type of antennas. Like for horn, I have shown you this wider mouth is the, it's a aperture type of an antenna, where this mouth area is the physical aperture. And even this paraboloid, you can see that is the aperture, physical aperture for this antenna. Okay. Now, as a note, you can see absorption ratio, or you can just denote it as V, small v. It is defined as the ratio of maximum effective aperture to the physical aperture, AEM divided by A suffix P. Okay, important one. Absorption ratio, we have seen effectiveness ratio, scattering ratio, two different as a note earlier. This is the third ratio, absorption ratio V, which is AEM by AP. This value is greater than 1 for linear antennas. What is linear antenna? This is a linear antenna. And the value is less than 1 for aperture type of antenna. See, paraboloid, horn antenna, all these are the what? Aperture type of antennas. Horn antenna, then paraboloid, and then helical probably. We have many antennas wherein the the aperture type is very important. Okay, for those the value is less than 1, and for linear antennas it is greater than 1. This is absorption ratio. And